So let's start our second day with the distribution of sticky notes. So I looked at the feedback of yesterday. I think it was reasonably good. One point that I wanted to make. Somebody said that the fonts were too small on the screen, so I have changed the font in RStudio. It should be bigger now. But please, something like that, tell me immediately. I really don't want you to struggle and read the gibberish I type, because it is gibberish when you're not used to it. So let's not make things even more difficult by having too small fonts. So please don't hesitate to, these are things that are reasonably easy to fix, and I can do it immediately. I don't know if the light is not good. I thought it was very hot yesterday at the end of the day. So if I had a red sticky note, I would have written, it's way too hot, please get the air conditioning on. Anyway, if there is anything that we can change immediately, let us know. Good. So, and somebody asked about creating custom templates in RStudio. So I found this post, RStudio project templates. And so apparently it's possible here to create example project templates. So apparently it's possible. I'm not an everyday RStudio user. It's not something I have ever tried, but apparently it's possible. I don't think it's probably not too difficult, but it's probably not totally trivial. Apparently you need kind of to define, the template. Apparently this is done in R. Here there is an index file that says, what to do and how to do it. But anyway, apparently it's possible, and I think it's a nice feature. And I googled, I don't know, RStudio custom template or something like this. So the next thing I'm going to do is to restart RStudio, unless are there any other questions? So I'm going to restart RStudio. And now RStudio, okay. So apparently it automatically starts where I closed it yesterday, or actually this morning. But in case that wasn't happening, I wanted to point out that I could always go to File, Open Project. Yesterday we started by creating a new project. So I can have, of course, multiple projects, multiple R projects for different scientific projects. And I could always navigate to this directory, rintro1, that's how I called my project, and then open this file, the rintro1.rproj. And now RStudio would restart in the proper directory that it corresponds to that project. Yeah. Now you're welcome to reuse the same project that we used yesterday, or start a new one as you prefer. So what we saw yesterday were vectors. We have seen, so vectors are linear objects, have a length. The smallest length we have seen is 1, but it could actually also be a vector of length 0. So if I numeric is a function. We see the parentheses, and if I say numeric 0, it creates a vector of numerics, of number, of length 0. And that's how it's reported, numeric 0. So vectors have a length. This length can be 0, but generally it will be 1 or it will be much bigger. This is a vector of numbers, but we have also seen vectors of characters or logicals, and we also have seen missing values NA. And that's one of the really powerful features of R, is that missing values are built in. NA is a special type. We have different types of NAs. We have NAs that match to characters, NAs that match to numerics, NAs that match to logicals, but we don't need to worry about that. R will handle that automatically. But always look up for missing values. In your data set, when you start your analysis, do you have missing values? It's extremely important to know. And maybe you have missing values. If you have a matrix with quantitative values, proteomics data set, it's very likely that some of the features haven't been measured in some samples. So it's very important to know. And if you don't have any missing values, make sure that you don't have suddenly missing values that appear, that pop up during your analysis. That points to something that went wrong, something unexpected that happened during your analysis. And very often you will get warnings in R. They show up in red, I think, saying warning, something happened. So make sure that you kind of keep track of the missing values. If they are there for a good reason, that's fine. But if suddenly NAs appear and they, in an unexpected way, it's better to stop there and kind of track back and understand why they appeared. We have seen functions with parentheses. And what we have also seen is the square bracket operator for subsetting. We haven't seen the function ls. ls lists all the variables that I have in my global environment. So I always pointed to this pane here that currently is empty. And if I create a variable x, it appears here, but I can also check what variables I have by using ls. And it lists a vector of characters of length 1 with the name x. Yes? Pardon, say again? Yes. So let me create y and z. Here they are. So I can delete 1 with rm and then the name of the variable I want to delete. So, yes. So how to delete all of them, and not by typing rm one by one. So if we use RStudio, we can click on the little broomstick here, and it will delete all of them. And later on, we will see, I'll start by explaining how to do one thing in R, in command line, and then later on we'll see how to do it in RStudio by clicking, which is more convenient. But I think it's important to know both ways, because you won't always have RStudio to run your analysis. If you have an analysis that takes a lot of time or requires lots of memory, you might have to run your analysis on the server, and you won't have RStudio. You might have, but you won't always have RStudio, so you might have to do things on the command line. So it's good to see that everything that we do in RStudio by clicking, by deleting, we can also do in the console. And actually, I like your question, how to delete all the variables. Well, we are going to delete all the variables by using a combination of ls and rm. So really what we want is, inside this rm here, to have the list of all the variable names that we want to delete. But this is something we can get with ls. So we want to rm. What do we want to rm? Well, actually, everything that is returned by ls. Now, there is only one thing, is that we need to specify that what we want to rm to remove is a list that is returned by ls. So this is how, in the console, by typing the commands, I can clean up my global environment. And look how beautiful this is. And it's again, kind of it looks obscure. It's a little bit of gibberish. So we need to focus on the anchor points that we know of and that can help us to kind of cut this long expression into pieces. So we have a parenthesis here, and we know parenthesis, that's Rm, it's the function. So we have a function, and then this long thing here inside the parenthesis, the input to that function is named. So we have named input, the named argument, list equal, and the value of this argument list is produced by another function. So the output of a function is used as the input to another function. Yes? No. No. If you delete everything, it's all gone. So everything in here in your environment is kind of temporary storage. If you close RStudio, it's deleted. If you delete them, there is no kind of trash can where you can recover them. But that is not a problem because we have scripts. So all the important R code, we write in a script. If we delete the variables, if we restart R, we have the script, we have the data, we can regenerate everything. Yes?
So why here this equal sign?
In here the equal sign? Yes. So this is not the assignment. Assignment would be an arrow or an equal. However, in this case, this is not an assignment. This is matching a value to a name as an argument, as an input to a function. In that case, you must use an equal sign. Let's try. Let's see what happens. Yeah. So sometimes it's possible to see that kind of syntax, but it can be confusing. This would mean on the fly create a new variable that you use as input to a function. That's why some people think that it's better to keep the equal for the matching of function argument names, like this, and use the arrow for assigning new, or creating new variable or assigning new values to variables. So I don't hear too well.
So we cannot change the name of the list to other names, right?
No. List. I should probably have shown question mark RM. Okay. RM, one of the inputs of RM is a list, and that is a character. And here it tells us a character vector naming objects to be removed. So the list equals is not something I choose, like when I create a variable, then I choose how to name the variable. The list is something that is defined in the RM function. And when you use something that is defined as input for a function, there is no choice, it has to be an equal. Does that answer your question? So we also have seen many other functions yesterday. And somebody brought that up in one of the comments. We have seen round, we have seen square root, we have seen R-norm, and there are many functions in R. The goal in this workshop is not to learn as many functions as possible, because we would all be bored. There are too many functions, it's impossible to remember all the functions. So some are important, and I will highlight them, and we're going to use them. But yeah, it won't be possible to kind of remember all the functions. But what is important is to remember question mark and then the name of a function to be able to go back and read the documentation. Okay. So we are going, however, to learn about a new function now, and this function is read.csv. Are you all familiar with CSV files? Could I have blue sticky notes for those that know what a CSV file is? And red sticky note if you would like me to remind what a CSV file is. So CSV stands for comma separated values. And, oh, sorry, yes. And I'm going to open one. No, where are my documents? Data. Okay. So there is this file called iprg_example_run_summary.csv that we are going to load and analyze in R. But if I open it here in Excel, this is how it looks like. I have a first column called protein with protein name, a second one log intensity, run, condition, bioreplicate intensity, and technical reference. Now, if I double-click on that CSV file, this computer is configured to automatically open it with Excel, okay, and display it like this. But actually, this file is not an Excel file. This file is a text file, as shown here. Can I increase the fonts? Maybe. Zoom in. Control. What was it? Control Shift Plus. No. View. Zoom. Oh, Control Numeric Plus. Control. What's numeric? Is this large enough? Yes. Okay. So the first line of this file says protein, log2 intensity, run, condition, bioreplicate intensity, technical reference. So this corresponds to the first row that we had in the Excel spreadsheet. The thing is that here we don't have cells. We don't have columns, but the columns are defined by comma. You see, you have protein, comma, log intensity, log2 intensity, comma, run, comma, and so on. So the comma represents the separation between columns. And then on the second line, I have the name of my first protein, Swiss prot index, blah, 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 comma, and then the value, so the second cell, if you want, after the first comma corresponds to log intensity. And then comma, another identifier that corresponds to, is aligned, if you want, with run. And then condition 1 that is aligned with condition, and so on. So this is a way to represent a text, so a spreadsheet using simple text markup. CSV for comma separated values, because we have commas that separate the values in a line that should be aligned to each other that come into columns. We could also have a tab separated format where the comma is replaced by a tab or semicolon and so on. Okay, so this separator here is an important, if you want, argument, important property of this text-based spreadsheet. And so what we are going to do is we are going to read this file, this text file, into R, into something that is a little bit like a spreadsheet. Now, it is possible to read Excel spreadsheets into R using a special package. There are several packages. I think one that is very good is called Read Excel. But we are going to focus on CSV files today. So I'm going to use read.csv. As the name implies, this function reads CSV files. So it assumes that these are text-based spreadsheets and that the separator is a comma. So not tab-separated files, not kind of semicolon-separated files, but comma-separated files. And the file that I would like to load is in my data directory and is called iprg summary.csv. And I'm going to read this file, and actually I'm going to create a new script, save it as script3.r. I'm going to write the code in here so I keep it visible on my screen. I'm going to put this on a new line just to save a little bit of space. So I would like you to run this command and put your sticky notes down, please, and put your blue sticky notes up. If here, it will appear here, you have a new variable called iprg, so that appears. That means that the command was run successfully and this new variable has been created. So read.csv reads a CSV file in. Load, we loaded, if I remember well, we used data iprg. It was this file. So this file has an RDA extension, and we will reload another RDA file in a couple of minutes. And that's for, RDA stands for R data. So that's a special R format, where you take any R object and you can save it on disk and then reload it without intermediate format like a CSV. Read.c, so you see it starts to outfill, so tap to finish read.csv, and then I open my quoting because this is a file name, and then I start to press data, tab, and then it auto-completes data because there is a data directory, and it's actually clever enough, or I can maybe tab again to auto-complete data, and then I start typing IP, and then it kind of suggests everything that is available. It's tab, yes. Press it as many times as needed. Now, for those that have the iprg variable, could you tell me what the class of iprg is? Using the function that we have seen yesterday, class, and then inside as input to class, use iprg. What have we created here? What type of variable is iprg? Data.frame, yes. So these data frames are, if you want, the equivalent of a spreadsheet. Let me know if when you type class iprg you don't get a vector of characters of length 1 that says data.frame. They are a little bit like spreadsheets with a few additional constraints that are very good. It's important to have sometimes constraints. So let me go back to vectors. Vectors are one-dimensional objects. And so they have a length, one dimension, and all the elements of a vector are of the same type. going to explain what the data frame is in a slightly convoluted way, but hopefully it will make sense later why I explain it like that. So a vector is a one-dimensional object composed of an arbitrary number of elements, and all the elements of the same class or same type, either all numbers, all characters. By the way, I didn't mention this yesterday, but for computers, numbers are stored in a different ways, whether these numbers are integers or floating numbers. And R is also aware of integers and floating numbers, but R will do the conversion automatically for us. We don't really need to worry about it. Okay, but so here's my vector. Now imagine we have a couple of vectors, all of the same length, and what we are going to do is that we are going to flip them. So from one vector that looks a little bit like a row, we are going to kind of tilt it and display it vertically, a little bit like a column of a spreadsheet. And now let's assume we not only have one vector, and I'm going to call this first vector protein, but let's imagine I have a second vector that has, and that is extremely important, exactly the same number of elements than protein. And I'm going to call that vector, what am I going to call it? I'm going to call it log2 intensity. And let's imagine I have a third vector that has exactly the same number of elements, and I'm going to call it rom, and so on. Now these are still vectors, so that the protein vector is a vector of characters. The rom vector is also a vector of characters, but the log2 intensity vector is a vector of numbers. So what I'm going to do with all these vectors is I'm going to paste them next to each other like different columns of a spreadsheet to give me a data frame. So a data frame is a little bit like a spreadsheet with these additional constraints, is that all my columns must have the same kind of length. Okay, it is not allowed to have one that is a little bit longer, which you can do in an Excel spreadsheet. You can type a little bit more at the bottom of a column. That is absolutely no problem for Excel. That would be a huge problem for data frame. It's not valid. It's not possible. The data frame must be of a rectangular shape. Yes?
So if you have a CSV file where it doesn't happen, you get an error, or is it substituting?
It will add an NA. And coming back to what I said before, you know your spreadsheet, assuming there are no NAs. If you read something in and you suddenly have an A, so you know something was wrong. So this is not allowed. A second essential property of the somehow convoluted way that I explained what the data frame is that all my log2 intensities must be numbers. It is not possible to suddenly have, an A in here, which is fine in an Excel spreadsheet. You can really type anything anywhere, and Excel will not complain. Excel will actually try to help you and convert G names to dates because they look vaguely similar. This is impossible to happen in spreadsheets because every element in that column, which is a vector, must be of the same type. So a data frame must be of a symmetric or a rectangular shape. Impossible to have a little bit more at the bottom or a little bit more on the side, little annotations. This is not possible. And why is this so important? Why is this good to have these restrictions? Because now I know that I can start to reason on this data frame. I know that, and so my data frame has two dimensions, rows and columns. And I know that whatever row I'm considering, if I take the second element in that row, I will always have a number. If I take the third element of any row, I know that I will always have a character in this case, a character that corresponds to what I had in my vector run. Yeah. So a combination of characters and numbers become characters. So here I only have numbers, and this is fine, is considered a valid number. If I only have characters, I have to quote them. It's a vector of characters of length 1. If I mix and match, I cannot just type it like this. This will produce an error. I would have to quote it. And now, although we are intelligent as opposed to a computer, which is not, we can see that in this character, in this string, we have letters and numbers, but that doesn't matter for the computer. Everything is quoted, so everything is a character. And so in these protein accession numbers, they are arbitrary. Again, the computer has absolutely no clue that these are protein identifiers. We know it. We know these are Swiss prot identifiers. We know that these are log2 intensities. We know that these corresponds to an important variable in our experimental design of the samples that we had. Of course, R is completely oblivious on this. But let's try to define a data frame a little bit more. Let's define the data frame, or the rows of the data frame, as... Can you see what I write here? No. I'm going to use that here. So here's my data frame. Beautiful rectangle with a set of columns. Every column is like a vector, contains the same type of elements, and then I have a certain number of rows. Oh, by the way, when we looked at the CSV file, the first row in the CSV file contained, we'll look at it later, contained the names of the columns. Retail CSV file takes this into account. So the first row is actually some data. It's not proteins or intensity of this row. Retail CSV expects the first line in my CSV file to be a header. So let's now assume that every row in the data frame is one observation. So the number of rows in my data frame corresponds to the number of observations I have in this data set. And along the columns, I have variables. So my first variable was protein, I had variable intensity, a variable run, variable biology replicate, technical component, and so on. So that means that any row that I take, or any two rows, are equivalent observations. So that for any row, the first element corresponds to the protein identifier. The second element corresponds to the intensity for that protein. The last element corresponds to the technical replicate. So I can reason on my rows. I take any row of that data set, and then I know exactly what I have at every position in that element. Similarly, any column that I take, for example, this column here, I know I have a variable. I know that I have intensities for all the proteins. I know that they're all the same element, the same class, in this case intensities, but in addition to that, I know that they record the same value, kind of the same quantity, which is an intensity. Observations along the rows, variables along the columns. And so if I take the intersection of a row and a column, I have one cell. And that is very important. I need to make sure when I encode my data in a cell spreadsheet, a CSV file, or anywhere, that cells contain only one piece of information. One variable that was recorded for one observation.
Do you have a list as a cell value?
You could, but that would break the kind of reasoning that we have here. You could imagine more complex data structures. And I will mention some other data structures in the paper. So yes, you could, technically you could. But here we would limit ourselves to these constraints because they allow us to reason. Because I know that if I take third row, third column, I have the ROM number for my third observation. And this is extremely powerful. Coming back to what I said yesterday, the data is too big to look, I cannot look at it. But I need to be able to reason on it. And these constraints are very helpful because they allow me to reason on the data without looking at it. So let me show you examples of bad data sets. Here is an example of a bad data set. So here we have dates. Here we have an index for plots. So these are from an ecological data set where they have different plots and they kind of sample species. Here's the weight of the animals they have sampled. And here, so a variable date collected, a variable plot, a variable weight. And here we have a variable, a columns, that doesn't contain one single piece of information. In these cells, we have two pieces of information. We have the species of the animal that was sampled and its sex. And they are kind of combined with a dash. This is problematic. Not because we would not be able to split this into R. Yes, we would. We are able to do it. The only thing is that we need to learn new functions, how to split characters. But we can't do any reasoning here on this data set. How many males and females have we sampled? It becomes difficult to answer this question. Before being able to answer this question, we will need to split these values. So to kind of fix this bug in the data, we would need to create a new column, let's say sex. We would have M, F, 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 M, F, and so on. And here keep DM, DM, DS, and so on. Okay? So this data frame kind of breaks the rule that each cell contains one and only one piece of information because this third column contains two variables instead of only one. Here is a rather extreme example of a horrible Excel spreadsheet. Where in one spreadsheet we have 8 tables. Well, when I say horrible, I'd probably be very mean here. It's maybe very nice from a human perspective, where I have kind of a summary of my 8 kind of data sets with a little bit of extra information here on the side. Maybe I might want to add some colors. But in terms of programming language, this is horrible. Because if I do read.csv on this file, what's going to happen? If I take this, the 19th row, I don't have an observation. And my different columns are not different variables. So if I had a data set like this, I would start by having to do lots of manual and restructuring maybe in different files or different sheets before I would be able to read it into R and start to do analysis. So there is no way to do any reasoning on this spreadsheet. So it's from an R perspective or a Python kind of a programming perspective, this is it's a bad data set, a bad spreadsheet. Now from a human perspective, maybe it's good because it allows to have a global overview, but it stops us from analyzing it in R. Yes, there was a question? So, for example, read from A2 to E18. Not with the standard tools. And it would be a big hassle to do. Yes?
Can you do multiple delimiters when you're reading the season?
No, you can have different types of delimiters, but they must all be consistent in the same file. Again, it would not be impossible to kind of scan the file and manually parse it with different separator. But that would be so much work unless you're already a very proficient R kind of user that it basically stops you from using R even before you can use R for what it's good, for analyzing your data, for doing your statistics, for plotting. You'll spend a lot of time parsing your data. And in my experience, that is the biggest hurdle for people to get started with R. It's the data is not well formatted. And they never get to the nice things, using R, which is, say, visualization and analyzing the data. So this is a big, this can be a big issue, how data is formatted. So the advice I have is try to keep your spreadsheets formatted like here, observations along the rows, variables along the columns, and one and only one piece of information per cell. And these are called kind of tidy. This is called tidy data. It's already cleaned up, and it's very easy, very smooth to read into R. So, as we'll do the exercise later. So how can we inspect these data frames? So we had length for vectors, but data frames don't have length. Data frames have dimensions. And they have two dimensions. The first dimension is the number of rows, and the second dimension is the number of columns. So this data frame, I haven't looked at it, but I know it has 36,321 observations, and each observation has 7 variables. What variables do I have? Well, here are the column names of my spreadsheet. I have a protein, log2 intensity, RON condition, bioreplicate intensity, technical replicate. If I have column names, I also have row names. And now this is going to be very long because there are 36,000 rows, 36,000 row names, and here they are. The row names are not very informative. They are kind of generated automatically, and these are the indices. Another helpful functions are hat that display the 6th first element of this variable. And in the case of the data frame, it's the 6 first rows. So I can't see the beginning of my 6 first rows. I need to scroll up if I manage to get. Here, so hat of IPRG, the 6 first values of proteins, the 6 first values of intensity, the 6 first values of RON condition, and so on. And if I have a hat, I also have a tail. Tail IPRG prints the 6 last elements. 2 other functions. str for structure. It tells me I have a data frame with that many observations and that many variables. And here it lists the name of my variables, protein of 2 intensity. It tells me whether these are integers or numbers. And here we have a factor, which is something we'll see a little bit later. And another one I want to mention briefly is summary. Summary of a data frame will give me a summary of all the variables of all the columns. So for example, here's a summary of my intensity. It tells me that I have minimum, a maximum intensity, here's my median, my mean, first quartile, and so on with intensities. Here, technical replicates are not numbers, so the summary will tell me that I have 1200 A technical replicates, 12,000 B replicates, 12,000 C replicates, and so on. Okay. So dim, yes.
So if there were missing values, what would the summary be?
If we had, okay, well, let's try this. R norm 10. Okay, so here I have X, and I'm going to concatenate X with an NA and overwrite my X. Oh, sorry. This will happen many more times. So if I say summary of X, summary is a special type of function. If I give it a vector, it will calculate the summary of the vector. If I give it a data frame, it will calculate a summary of all the columns. And here it tells me, here's the minimum, the maximum, and so on. And it tells me that I have one missing value. So if I had missing values somewhere in my intensity, here I would have another row saying NAs and the number of NAs present. So I'm going to type here dim and row and call, what else did I have? Hat, tail, call names, row names, and I would like you to try these out. These functions, str, summary. Here are all the functions that I would like you to try out on this IPRG data frame that you have. Or names. If you use call names or names, it's the same. You will get the same output here. So could you try this with IPRG and make sure? Oh, and then there is also class. Okay. Make sure you figure out what the class of IPRG is, how many rows you have, how many columns. What the variables are, and so on. And remember, the number of rows corresponds to the number of observations, the number of columns to the number of variables. Okay. And could you take the sticky notes down and blue sticky notes up when you're happy, when you have explored something. And for those that have finished this exercise, I would like you to do the following. I'm going to type it here. Load load the iprg2.rda file. Okay, if we look at the extension, it's not CSV, it's RDA. So we need to use the load function like we did yesterday. So once you have familiarized yourselves with these functions to describe a data frame, again, we don't look at the values. We look maybe at the head, at the tail, some random values here and there. We check for NAs. But we need to become comfortable with the fact that we don't see all the data. We learn properties of the data. And then we will do some reasoning on these properties. Once you have familiarized yourself with these functions, could you load this iprg2 RDA and explore it with some of these functions and figure out what this data is? Well, based on the name, it's also this iprg data set, which is a proteomics data set that Mina can tell you about. It's from one of her papers. But how is this data set, this iprg2 data set? It stands for R data, RDA, or it could also be capital R, capital D data. And by the way, after loading iprg2, you can use ls to see what new variable was created in your working environment. So do the same thing, exploring the data set with this new iprg2. That is different than frequency. Frequency is and then it returns what it has read. So this load so the load you don't need to store the variable. Because the variable appears in the working part, so the variable appears automatically. So it has a return value. That return value is a value. Yes, that was a kind of another side discussion. So load. Okay. Imagine this is a world environment where all the variables exist. You have variable rocks, and you have variable. You say load Laurent with RDA. Okay. I'm not there. I'm quite on the hardwire. You call Laurent with RDA. You type load Laurent RDA. I appear you work. You don't need to do anything else. If I was to see speed and you type frequency speed, Laurent was speed. Frequency speed function. Reading this and returning is not as a variable. That's the content as data. And if you don't do anything else, I show up on your console, I print it out, and then I disappear. And then you won't see it. So you know that this is variable. And in that case, you need to redirect all the things to variable. This depends. This is something that is it's your collaborators use on. That's actually useful to collaborate on projects. And maybe they're doing some analysis. They want to share some of the results. Then it's also very useful to store results on the RDA file. If you have RDA files, so there are Spreadsheets. Some people want speed file, for example, say France and Belgium and Germany use constantly for testing. 1.000 for somebody from France, it would be 1.0. There are these two things that are stored as not with an RDA. An RDA knows it's 1,000 or it's 1. So there is no simply mates. States, so one state here, which I find very confusing. I always so now if I send this to the D file, 01012010, and I'll use 01022010 is the first, I would say, well, it's the first comparison. It's the second generation. RDA file. The possibility that you can store data and the energy analysis but it will sound So, who can tell me what? So, the question, what is the difference between read.csv and load? Shouldn't have taken this. So, read.csv reads a CSV file. On this, you have a comma-separated file. Read.csv will parse the file, take the first row, split the first row based on the comma, and do this for all the rows, and then create a data frame. And the data frame the data frame is then returned from the function and printed on the console. But it's kind of lost for me. I can see it, but it's not stored. So with read.csv, it returns a data frame. I would then kind of store it into a new in a new variable. CSV file. Read.csv only works for CSV files. By the way, there is also read.delim to read tabbed limited data. There is a read CSV2 for semicolon separated files and so on. We'll look at the documentation right later. Now, load only works with RDA files. RDA files are, if you take this object in R, any kind of object, not only a data frame, anything, it can be a vector, and other things that we haven't seen yet. And we take this R representation in memory of your computer, and you write as it is on disk. So it's a binary file that we cannot open with our editor and look at. It's kind of a compact representation of this R object in memory that is written to this. And what we do with that one is that we load it. We don't read it, we load it, and it kind of automatically appears in our working environment. That's why I load data IPRG2, and now I don't need to redirect the output of that function. IPRG2 automatically appears in my workspace. Okay? And I have to apologize because yesterday I was very tired, and when I gave the exercise I mentioned, save, use load and store it in a variable. You don't need to do that. Load will load that variable and automatically kind of expose it in your workspace. Yes?
So IPRG2 is a variable now. So IPRG is a variable.
Yes, that is a variable. So let me delete it. Alas, IPRG2 is not there, and then I load this file. By the way, in this case, and I would advise you to do that, the variable that is saved in that file is called IPRG2, and I named the file IPRG2.rda. I could have named the file anything else. I find it very useful to use the file name, matching file names and variable names. But there is no guarantee that the file is called IPRG2, that the variable that is loaded is called IPRG2. But here we go. Okay, so two different things. Yes?
Do you need the dot backslash?
No, you don't. This would also work. The dot means this directory, and in this directory, look for data directory. I may be just being a bit pedantic. This means look in the data directory. I don't specify starting from this directory. And yeah.
Sorry, when
Yes.
you say this directory, you mean the working directory?
Yes.
If you had a different one, you would just point it to a different one instead of dot.
Yes, absolutely. And how do I know what is my working directory with getwd, and it tells me my working directory. And so if I wanted to load a file that is not in my working directory but is in my documents directory, I would use two dots. Two dots means go kind of one directory deeper. So from R intro to dot means now I'm in documents. And then, assuming I have another data directory in capital, all capitals, I would type like this. So who knows what is stored in this IPRG2? Can anyone describe what I have in our IPRG2? Yes?
So, I guess examples are mass spectrums. So like 12, so 12 is total, there's like, I guess 4, and each is like, there's like 3 replicas, for example. So like that's a list of proteins that I guess is 2,000 or so rows long, and each sample or run has a measurement for each row.
Yes. Absolutely. So, so names IPRG. So I have proteins. I have intensities for different runs, different mass spectrometry acquisitions. If I look at the names of IPRG2, here they are. These are all my runs that I have now used to create columns. And my row names of IPRG2, and I'm going to look at the head of these, because otherwise I have too many, corresponds to my protein identifiers. So each element of a cell here is one intensity. So it's a different representation of the same data, except that here I focus on proteins by samples, and in the other case I have 7 variables: proteins, samples, intensities, biological replicates, technical representatives, and for each line I have kind of these 7 pieces of information. Okay? So we have different ways to format, to structure the data. And there is no better format, depending on what we want to do. Some are better than others. So we have seen subsetting for vectors. Oh, sorry. Any questions about IPRG and IPRG2? Can I carry on? So we have seen the square bracket operator for subsetting vectors. Yes, X. Third element. Or X, I want the third and the 8th element. Here they are. I do my subsetting with a square bracket operator. Vector is a one-dimensional object. Data frames are two-dimensional objects. IPRG, I want to subset IPRG. I use my square bracket operator, but I have 2 dimensions, so I have to add a comma to do my subsetting along 2 dimensions. My first dimension is rows or observations. So for example, if I want to subset rows 2 and 4, I use C24 before the comma. This produces a new data frame that has still 7 columns, 7 variables, because I didn't specify any subsetting here, but it only has 2 rows, indices 2 and 4. I still use the square bracket operator with a comma, because I have 2 dimensions, as opposed to a vector that is a one-dimensional object. Before my comma here, I can use indices or logicals, or characters, as we'll see in a minute, to subset the rows. Yes, very good. IPRG 1, 2, 3. That is my first observation, my second or my third observation. As you can see, protein log 2 intensity and so on. So the first row in my CSV file has automatically been converted to the names of my columns. Let's have a quick look at read.csv. Read.csv, actually there. Read.csv. I'm sorry, I don't know if it's possible to increase the font of the documentation. Here's read.csv, read.csv2, read.delin, read.delin2, and the very general function read.table. All these functions can parse text-based spreadsheets. And as you can see here, there are many arguments that help us fine-tune these functions. And one of them is header. So if we look at read.csv, header equals true. So if you use read.csv, it assumes that the first line of your CSV file is a header. If you did not have a header in your CSV file, you need to change it to header equals false. And then your first line would become your first observation. Another important parameter is sep, separator, which in this case is a comma, because it's read.csv. Read.delin, the sep is \t, which is the symbol for tab. Yes? Sorry, view, zoom in. Ah, yes. Thank you. Thank you very much. So is that large enough? Yes? Okay. I do not want to see a red sticky notes telling me that my fonts of my documentation file were too small. No, if they're too small, let me know. Now or later. So here we are. Header equals true, separator is comma. If we have read.delin, the separator is a tab, and so on. So you can use these functions to really parse different types of text-based spreadsheets. And so to come back to the question, yes, read.csv automatically uses the first row of my CSV file as a header for my name, so my call names of my data frame, and then I start with my first observation, that is the second row in my CSV file. Okay. So back to my subsetting. Indices before the comma is to subset rows. Indices after the comma is to subset columns. So I'm going to call head of this. Head of this returns a new data frame with 3 variables, 3 columns, protein, log2 intensity, and raw, my 3 first columns. Yes?
When you read your CSV, can you set the row names?
I don't remember whether you can do it. I think you can do it when you read a CSV file. Maybe there is something called row names, and then you give the index of the column. But that's also something that we can do afterwards. So IPRG, show me the 3 first rows and the 3 first columns. So I have kind of mini data frame, 3 by 3. And now it becomes possible to look at the data, kind of bits of the data. Now let's say that these actually look, no. I cannot use these as row names, because row names must be unique. So, temp, IPRG 1 to 10, 1 to 3. So I create a smaller version of IPRG for the 10 first observations that only contains the 3 first variables, and I store this into my temp variable. Here's temp. Row names of temp is 1 to 10, not very useful. I can set my row names of temp to letters, capital letters as we have seen yesterday, but I subset my 26 letters to my 10 first letters because I have 10 observations. And if I look back now at temp, here are my row names. So this is something that I can do while I read it in or afterwards. And row names of temp now are my letters. So this is a very important syntax. Just if I only use row names of temp, that's a query. I ask what are the row names of temp. If I use row name of temps and then I assign this to something, then it's kind of a replacement of the row names. And that's a pattern in R that we are going to observe many, many times. The TMP variable is one that I created here. It's a smaller data frame to illustrate updating the row names. Yes?
What is the difference between what you just wrote and what you wrote before, which was in parentheses with this? You had C24.
Yes.
I might have explained it yesterday.
Yeah, it's no problem. 1 column 3 creates a sequence of integers starting at 1, finishing at 3. 1 to 3 and so on. I could do 1 to 100. So instead of typing 1, 2, 3, if this is exactly what I want, the shortcut is 1 column 3.
And you don't need to put the C. The C
No.
is not a column or anything like that.
Yeah.
That's where I'm having trouble with. What is the C before the parentheses?
Because that's a function C that concatenates 1, 2, and 3.
Okay.
This is a special syntax because creating a sequence is something that we do very often, and so there is this special syntax there. And and we're going to finish on, so here, subsetting along the columns, subsetting along the rows. We can subset both. Now, if we wanted to have one variable in particular, let's say the first variable, let me names IPRG. Yeah. So if I wanted to have my first variable, my proteins, I could type IPRG1 like this. But if I want to have the protein and I type IPRG1, that relies on an assumption, and that assumption is that my first variable is protein. This is the case now, but that is still a strong assumption. So that it's also possible to do the subsetting by name. Okay, and now I don't need to check that protein or where protein is in my data frame. I name it, and this will extract that variable. So here are all the protein names. There is another syntax for this, because this is something that we end up doing very, very often, extracting one variable, and the shortcut is to use the dollar operator. So let me write it here as a command. These two are the same. This one is easier to talk. So I suggest we have a little break, and I will prepare a little challenge. Is it 30? Mina, is it 30 minutes? Yes. So there are, I think, refreshments outside. So when you come back at 10:30, I'll have prepared a little challenge for you to practice the subsetting of data frames.